Hello everyone. Hi, I'm Sampriti, one of your TAs for this course coming semester, and I'll be taking Recitation 0J Part B, which is on data preprocessing. After seeing Part A, you might have an idea of what data preprocessing is. In this particular part, let's have a look at why we need data preprocessing and how we can preprocess the data. The data which we collect can have a lot of outliers, and the ranges of the feature values might not always be the same. Like most of the times, it will not be the same actually. So, uh, it can also have a lot of redundant or unnecessary features which will not be very useful while training. The format in which we get the real data is also not always being understood by the machines. For example, you have like non-numerical data. Apart from like the data which you have, even the distribution as per the classes might not be very even, and for such cases, it will introduce some biases. There is also a possibility of having like missing values or incomplete rows, which can lead to unnecessary problems. So, to deal with all such problems, we need data preprocessing before passing this to the model. Let's dive deeper into it and see how we can deal with bad data quality. So as I was previously saying, the features which you see might not have like the same ranges. Let's take a simple example of like predicting house prices. For example, let's say you have area and number of bedrooms as your features. So area is going to be very large as compared to the number of bedrooms, but you do not want your model to have this unnecessary bias over the area. So for such cases, it is very important to scale and normalize your data before passing it further. It is fairly common to see that the data is collected from different sources and can have some mismatch in the data type. For example, maybe you're working for like some international trading firm and dealing with financial data, but the data can have different currency values corresponding to different countries. So you need to fix a standard and convert everything as per that. If you have like missing values in your data, it can be dealt with in two ways majorly. One is to impute the values based on the other row information. So in such cases, you can either take like mean of all the values for that particular feature or average it out. It is also possible to have like sequential data, and for such cases, you can directly copy the value from the previous or the subsequent rows. If you have sufficient data, you can actually ignore all this hustle and like remove the entire row for corresponding to the missing values. But make sure that you have enough data before doing this because it's never a good idea to lose upon data. You might also have to clean up the data which you get, which is remove unnecessary things that are not adding any information. For example, for text or speech data, having sounds like or are not really important, and you can remove those instead of confusing the model. Let's see what problems can be caused if you have a lot of features. So high dimension means having a lot of features, and you might see that not all the features are really important for the model to train. Some features can have multicollinearities, and in such cases, you can just keep one of those. If you have noisy attributes, that is noisy features, you can remove those rather than confusing the model with noise. Not just having bad features, but having a lot of features also leads to a problem called as curse of dimensionality, which is that in this higher dimensional space, the points are not really close enough and the data that you get is sparse for the model to generalize well. So there are several ways for reducing the dimensions, but one of the most important way, or like the most used way, is to have some feature correlation between the input features and the target you're training for, and set a threshold and remove all the features that are not really important for the model. Sorry. So here is a diagram which gives a better understanding of the methods available for reducing dimensionality. Roughly, we can split it in two parts, which is like feature selection and creating new features. For feature selection, you can have filters that would remove the features. For example, have a filter on number of missing values. And if there are a lot of missing values, you just remove that remove that feature, sorry. Another thing can be to use forward feature selection, which is to start training with one or less number of features and keep on adding the features which affect the accuracy the most. The reverse way of it is backward elimination, where you train your model based on all the features you have, and that sets your bar for the accuracy, and then keep on removing the features that do not really drop the accuracy that much. Going to creating new features, there can be various linear and nonlinear methods for this. So in nonlinear methods, you can have a function or like a kernel function that can combine multiple features and create a new feature out of it. For example, r is equal to x square plus y square. For creating such functions, you can visualize the data or understand the trend, which will actually combine multiple functions into one. But if it gets fairly complicated, we have methods like autoencoders, which are neural networks that learn themselves and create lower dimension vector for you, and you can pass that as your input further. We'll learn more about autoencoders as we proceed during the semesters. Some linear methods worth noting are like PCA, LDA, SVM, which are out of scope for this particular course as such, but it's worth mentioning and you can have a look at them. They help you select important features out of all those, and then you can just have that subset passed further. Coming to data leakage, in part A, you got introduced to what data leakage is. It's basically having some part of output or information in your input which might not be present during your inference time. So it is very important to deal with data leakage, because otherwise you will train the model which has like what's best accuracy, but when you go on testing it, it will not perform that well. So how do we deal with data leakage? You can actually um, yeah, remove features that contain information about the target which might not be available during inference, which means that, for example, let's say speech data, if you're trying to predict what the next word is going to be during the input, during the training phase, you have the entire sentence, but passing that entire sentence is actually letting the model to cheat and not helping, because you will not have the entire sentence during inference. So another thing to do is to have a separate validation and test train data set. So that will give you a better understanding of how your model is going to perform on unseen data during the training phase itself. Sometimes when you do not have a lot of data to create three different splits, you can use methods like k-fold cross-validation. It is very, very important to know that always split your data into train and test before you normalize it, as you do not want to calculate your normalization parameter on all the data and give some hints to the model or some information to the model about the test data as well. So instead, you split it first and calculate your parameters only on the trained data set and use those normalization parameters for your test data set. So dealing with categorical data. Categorical data is like all those non-numerical data values. For example, if you have like season as one of your features, it can be rainy, summer, and winter, for example. So these words do not actually mean anything to the machine, and we need to convert them to some kind of numerical values before passing further. That can be done by directly mapping those to some unique numbers, which is like the most straightforward way to do so. But this might introduce some bias due to ordinality. So, for example, you do not have any relation between seasons, but when you convert it and map it to 0, 1, and 2, the model might learn that there is some understanding, like some maybe 0 is greater than 1 or 1 is equidistant from 0 and 2. So such kind of ordinality understanding can be learned by the model, which is not really true for the real world data. So a better way to deal with this is to create one-hot encoded vectors, which is to have a vector of size equal to unique features, equal to, sorry, unique values for that particular feature, and have one in just in a place corresponding to that feature. So feature hashing is also one way of doing so, where you have a function that takes in your input and like converts it to the numeric value. It is used generally for larger data sets or where you need data encryption because the function is actually hidden. Having class imbalance is also a fairly common problem, which is, for example, like you have just 10 instances for class A and 90 instances for class B. In such cases, when you sample the data, it will not have like equal number of instances from each class and cannot can learn or have bias towards class B in this case. So to deal with it, you can either oversample from class A or undersample from class B. It's ideal to have like uniform distribution to do so, but in real world, perfect balance might not always be possible, or it might not be necessary. So in such cases, you can try to have some realistic balance or distribution of classes, wherein if you want a particular class to be more important, have more data from that class. Dealing with class imbalance can also be done by having a weighted loss function. So you will learn more about what loss functions are in the course. But for now, to have a basic understanding of it, it's basically having weights to reduce the error more for class A and less for class B, as you have less number of instances corresponding to class A. Now that we have seen what can be the problems in the data and how to pre-process it, let's have a look at what libraries can be used to do so in Python. There are multiple libraries that support data pre-processing, but in this particular course, we will focus more on PyTorch. So in PyTorch, you get APIs and functions to implement all the data pre-processing steps that we just discussed. So you can have functions for like random sampling, weighted random sampling if there is class imbalance. You can use Lambda function and define what kind of data cleaning is required and then apply those filters to your data. There is also support for splitting or shuffling the data. So here you see data augmentation as well. So data augmentation is not actually data pre-processing, but it's most widely used and you will be using it during your assignments and also in like every time you encounter any neural network training. So a data augmentation is to increase your data or have diverse data by making some tweaks to the data set you have. For example, like in case of images, You can crop the image or scale the image, flip it, rotate it to just create more variations in your data set. Here, I have specifically mentioned uh, the support PyTorch has for image and audio data set because that's the kind of data you will be dealing with in your assignments. But data augmentation goes far beyond that as well. So data preprocessing and data augmentation is implemented while writing the data loader class in PyTorch, and you will learn more about the implementation and syntax of it during the data loader recitation and as you write your own data loader. But for now, you can have a look at the link given in the slides. Some other libraries worth mentioning are scikit-learn, pandas, numpy, which also have a lot of support for all the data pre-processing, things like random splitting, applying filters, normalizing, etc. So with this, we come to an end for the part B of this recitation. In part C, Abu will introduce you to speech-related data pre-processing. Thank you so much.